Hello again. This is Ismail Badran, your chemistry instructor for Chemistry 101. Welcome again to the course, and this is the second lecture in the first chapter. So I hope that you are doing all well. Last time we introduced the course and we also talked about a little bit about chapter 1, the study with change. We talked about measurements, and I think we covered some important aspects in measurements. We talked also about the SI units. This table is important. Is an important table. It has to be memorized, and the SI units of different measurements. This table is as well is important. How to go from kilo to mega to micro to milli, and I hope that you had the chance to practice some exercises to solve some of this table. We talked also about mass and weight and the difference between mass and weight, and we also talked about volume and how to change between volume units, the difference between liters, milliliters, meter cube, and all of that. Today we continue our discussion with talk about density. So density in physics is defined as the mass over volume, or simply D is equal M over V. Usually I'm not a fan of using D for density, so density is usually referred by rho. Rho is a Greek letter. Okay, it means density. So we say rho is equal mass over volume. So usually the mass in the SI unit for measuring mass is a kilogram, and the SI unit for volume is meter cube. So that would be the SI unit for density is kilogram divided by meter cube. However, there is another common unit for measuring density, which is gram per mil. But one kilogram per meter cube is not equal to gram per mil. You might need to work out the conversion factor between the two, and I will leave this as a homework for you. What is the conversion factor between gram per mil and kilogram per meter cube? Now, densities of material are different. So density of water, everybody knows it's 1. So it's 1 unit, 1 gram per mil. But some materials, they have less densities. So for example, wood, it has a density of less than water. That's why wood flows over water. While some other materials, like iron, mercury, and gold, metals, they have higher densities. Especially mercury, it has a very high density. This question here speaks about density. Let's read the question. Gold is a precious metal that is chemically unreactive. It's used mostly in jewelry, dentistry, and electronic devices. So usually these questions tells you a story that might not relate to the question itself, but the question starts here where it says a piece of gold ingot with a mass of 301 grams or 301 grams has a volume of 15.6 centimeter cube, or in other words 15.6 milliliter. Calculate the density of gold. This is a straightforward question. We move on and say example, I think that's example 1.1. Yes, example 1.1. So we are giving the mass. It's always good to write what is given, 3101 grams. We have the volume, which is 15.6 centimeter cube. Cubic centimeter. So, and we need the density, or I will say rho is equal 1. So here I'm organizing my solution, putting the data given, and also what is required in the question, and we proceed by saying rho is equal mass over volume. 301 grams. It's very important that you put the units in your answer. We are not in school anymore, we are in university, so you must put the units. If you divide these numbers, you get an answer of 19.29 something. I will round this to 19.3 gram per centimeter cube. So we will talk about the rounding and why we round this, and usually we put this in a box later on. So we're going to talk about significant figures at the end of this lecture, but usually we put this, we round this number to the correct number of significant figures, and we put it in a box for teachers to mark for us. As you see here, the answer is composed of two things: the number and the unit. Okay. So if this question is worth 3 marks, let's say in an exam, the formula has 1 mark. The substituting the numbers with the correct units, that will also another mark. This would be maybe, so this is 1, this is 1, this is maybe 0.5, and this is 0.5. Okay, so that will be your 3 out of 3. So you must put the unit at the end of solving a question. If you notice the book and you go to example 1.1 in the book, I'm just going to show you a better way to study here. So if you scroll to example 1.1, this is the example. It's solved already in a book, but the most important thing is that the example is followed by a practice exercise. Here it says a piece of platinum metal, so and so. So it's always good to solve these practice exercises right after the class, so you practice solving exercises and the idea gets direct to your head. Okay, the answers for these practice exercises, as I said last time, it is also in the at the end of the chapter. So if you scroll all the way down to the end of chapter 1, you will find the answers for the practice exercises. Okay, so that's about density. Here another question: density of mercury, the only metal that is liquid at room temperature, is 13.6 gram per mole. Calculate the mass of 5.5 mil of the liquid. So that's another question. We can do it easily here. So just gonna write a line. So example 1.2. I'm provided the density of mercury. It's 13.6 gram per mil, and I have also he said volume 5.5 mil. So the volume is 5.5 mil, and he needs the mass. Okay, so again I can use this. I can say rho is equal to mass over volume, and you know this, right? I think you know this from school. You can do this. So density is equal mass over volume. So you can say the mass. So the mass is equal this, right? So the mass equal rho times volume. So rho times volume. Okay. Just stick to my red color here. So you can proceed by saying. So you just multiply these two things. So 13.6 gram per milliliter times 5.5 milliliter. And you see how beautiful is this when you write the units, they cancel out easily, okay? And you are left with the gram, right? So you just multiply these numbers. 13.6 times 5.5, it's 74.8, 74.8 grams. That's the mass in units of grams. So we're doing good. Just easy question, fantastic question. Okay. Temperature. We said that temperature is, the SI unit for measuring temperature is Kelvin. However, there are other units to measure temperature. Usually we use Celsius in the Middle East to say that temperature today is 50 Celsius or 35 Celsius, whatever. In other places in the world, they use Fahrenheit, which is another unit to measure temperatures. Like the United States, they say the temperature today is 80 Fahrenheit. That might be a big number for us, but Fahrenheit does not equal to Celsius. So there are conversion factors between Kelvin, Fahrenheit, and Celsius. The first conversion factor is the Kelvin is equal to the Celsius plus 273.15. So 100 Celsius, for example, would equal to 373.15 Kelvin. Also, we have a conversion factor of Fahrenheit to Celsius. The Fahrenheit is equal 9/5 Celsius plus 32. So you can use that to convert between Celsius and Fahrenheit. For this course, for Chemistry 101, we are only asking you in the exams for the Kelvin to Celsius. The Fahrenheit is just for your general knowledge, okay? So again, in this course, you are required to answer questions to convert Celsius between Celsius and Kelvin. But for the Fahrenheit, we're not going to ask you about that. It's just for your general knowledge. You can use that formula. You can notice here that I'm putting we're using a small degree subscript to the Celsius and the Fahrenheit. So we say the temperature is 50 degrees Celsius or 50 degrees Fahrenheit, but we never do that for the Kelvin. And the reason behind that is that the Kelvin is an absolute scale. So when you say 0 Celsius, there is something below that 0. We have minus 10, minus 20, minus 30, minus 200 Celsius. And the same thing for Fahrenheit. But there is nothing minus for the Kelvin. The 0 Kelvin is the absolute temperature. And theoretically, it's impossible to go below 0 Kelvin, at least at the theoretical level. And therefore, there is nothing in the minus Kelvin. There is nothing called minus 10 Kelvin or minus 20 Kelvin. So note that the Kelvin scale does not have the degree sign because it's an absolute. So we say 10 Kelvin, 20 Kelvin. We don't say 10 degrees Kelvin. And temperature expressed in Kelvin can never be negative. And that's what I just said last time. I will leave you to practice this question in your free time. I think it's an easy, straightforward question to convert between temperatures. Okay, now let's move on to handling numbers. In this instance, we're going to talk about two things. We're going to talk about scientific notation and significant figures. You might ask yourself, what is the difference between these three numbers? 16.43, 16.430, and 16.4300. Are they the same? Well, they look the same, but probably they are different in accuracy. And as I said last time, the number of decimal places that you add to the right of the number depends on your instrument. So some balances, for example, some scales in the lab, they have 2 digits, and that will give you 16.43. But some other scales, they are more accurate. We have 4 or sometimes 5 digits balance that will give you a more accurate answer. And this brings us to the same example as I gave you last time when I say what is the length of the room that we are sitting in. You can say, okay, the width is 3 meters, and somebody else comes and says, okay, it's 3.5, and a third person comes and says, okay, it is 3.56 meters. Those answers depend on the instrument and the device they use to get this measurement. The more accurate the instrument, the more accurate the number is. Now, before we jump into significant figures, let's talk about something you already know, which is the scientific notation. We have a huge number here, the number of atoms in a 12 grams of carbon. There is like 602, and there is a bunch of zeros here. That probably you know it before. It's the Avogadro number. So it's kind of a heavy job to write all of these zeros every time when you do the mathematics. That's why we use the scientific notation. And we can just express this number easily by saying it's equal to 6.022 and times the number of zeros next to the number 6. So that would be 6.022 times 10 to the 23 atoms. And this is called scientific notation. Okay? So when I say 10 power 23, that's a huge number. And when that exponent is positive, that means it's a big number. When the exponent is negative, like in the other case, when it says the mass of a single carbon atom in a gram is this, 1.99 times 10 to the minus 23, this means it is extremely small number. So common understanding is that a positive exponent, when I say 6 times 10 to the power 4, for example, that means 6,000. And 6 times 10 to the power minus 6, that means it's a smaller number, smaller than 1. So in scientific notation, all numbers are written in the form of m times 10 power n, where m is the number itself and n is the exponent or the integer. And just throwing some quick examples here. 568.762. So you see here a quick note on reading the numbers, by the way, in the mathematics in English language. When you read a number like this, 568.762, you read the number as it is, as we usually know before the decimal point. So it's 568. Anything after the decimal point, you read as numbers. You don't read it in hundreds and thousands. So you say 568.762. You don't say 568.762. Okay, that's wrong. And the number to the right here, it's equal to 0.0000772. This is the way you read it. So again, going back to the scientific notation, if you want to write this down, number 568.762 in scientific notation, you just move in the decimal point 2 spaces to the left, and that will be 5.687862 times 10 to the power 2. That's because you moved the decimal point to the right, to the left. If you want to move it to the right, as in the second example, you see here we are moving it, if you count the numbers, if you count the spaces, that we're moving it from the first place to the between the two sevens, okay? Between the two sevens. So that would be 7.72 times 10 to the power minus 6. So you can practice this as well. Now, the question comes in when we solve chemical problems is what type of answer should we use from the calculator? You know, when you multiply things in the calculator or you add things, the calculator will give you a big number. So do we write all the numbers? Of course not. We have to stick with some rules that allows us to write the correct answer and the correct number of significant figures. So now we need to also deal with scientific notation, addition and subtraction. So we have two cases here. We have a case A in addition and subtraction of scientific notation. In this case, if we throw up an example here, 4.31 times 10 to the power 4 plus 3.9 times 10 to the power 3. Now you notice that here we are adding two numbers with different exponents. But that doesn't matter in the case of addition and subtraction. What we do here, we just add the m's, which are the numbers 4.31 and plus 3.9. Okay, and now we need to deal with scientific notations when we add or subtract or multiply even scientific notation numbers. So we have two cases here. In scenario A, we deal with addition and subtraction, and we're going to throw up an example here, which is 4.31 times 10 to the power 4 plus 3.9 times 10 to the power 3. Now for this example, which is I'm going to just transfer here to my whiteboard. So here I have 4.31 times 10 to the power 4 and plus 3.9 times 10 to the power 3. So here, my friends, you can answer that easily by using calculator, but in case you don't have a calculator, the way you do this is you look at the smallest exponent, okay? So that's a 3, that's 4. You need to make the exponents the same first. You want to unify the exponents. So the way you do this, you keep this as is, 4.31 times 10 to the power 4, okay, plus, and you want to change this into power 4. And the way you do this is you want to make this a power 4. That means you want to move this decimal point here. So that would be 0.39 times 10 to the power 4. So the exponents are the same. Then you just add these numbers up now. Okay? So 4.31 plus 0.39, that would be 4.7. So 4.70 times 10 to the power 4. There is a rule that says how many significant figures that you can put here. We're going to come to this rule up, but now let's focus on unifying the exponents. So you cannot add actually numbers with different exponents or subtract them. You have to unify the exponents first. That's for addition and subtraction. So the steps here, you need to identify the number with the smaller exponent and make it equal to the number with the larger exponent by changing the positions of the decimal point. That's the procedure to do this. In multiplication is easier because in this case what you do is you just multiply the numbers and you add the exponents, okay? So 4.0 times 10 to the power minus 5 times 7.0 times 10 to the power 3. What you do here is you multiply the 4 times 7 and then you add the exponents. So minus 5 plus 3, that would be minus 2, and the answer will be 28 times 10 to the power minus 2. Because 4 times 7 is 28. and minus 5 plus 3 is minus 2. So the answer will be 28 times 10 to the power minus 2. But the problem is, this is not a scientific notation. 28 times 10 to the minus 2. That's not written in scientific notation. What you need to do is, this scientific notation means we have to have a decimal point between the 2.8. So that you convert that to, if you want, this is the decimal point here, just move it to the left one space, so that would be 2.8 times 10 to the minus 1. And in division, just like in multiplication, you divide the numbers m1 divided by a2 and you subtract the exponents. And throwing an example, 8.5 times 10 to the power 4 plus 5.0 times 10 to the power 3 to the power minus 9 to the power 9. Sorry, you divide 8.5 divided by 5. That would be 1.7, and then you subtract the exponent. So 4 minus 9 is minus 5. So the answer would be 1.7 times 10 to the minus 5. There are different types of questions in the book, and also in the online exercises. So please practice this. It's easy mathematics, just to review, just to refresh your mind on dealing with scientific notations. Solve as many questions as you can, and also discuss this with your friends. Now moving on to an important, a more important actually aspect of numbers, which is the significant figures. Now, what is meant by the significant figures? Significant figures refer to the number of important significant digits, 0 through 9 inclusive, and the coefficient of an expression in scientific notation. And here we throw this question again. When we say 16.43, 16.430, and 16.4300, are they the same? They look the same, but as I said, some of them are more accurate than another. Now let me explain to you what is exactly meant by the significant figures. When I ask you what is the mass of something, what is the mass of your mobile phone, and then you use a balance and you say okay, it's 43 grams 0.6. Okay, now, and I said, are you sure? What do you say? Okay, I am sure about the 43, but I'm not sure about the 6. Because it might be 5, it might be 4, it might be something. So usually a measurement is composed of two things. It's composed of certain numbers, so that you are certain about these two numbers, and you are uncertain about that. Okay? Now it doesn't matter the number you are uncertain about. The number of significant figures, we call them Sig Figs, just to significant figures or Sig, is equal to the certain plus uncertain. And in this case, in this example, in this specific example, they're equal to 3, okay? Because we have two certain and one uncertain, so it doesn't matter, 3. But what about this number here? We have 0.0035. What about this example here? How many significant figures do we have in this question? Some people will say, okay, we have 1, 2, 3, 4, 5, and some people they have, we say 2. Well, it's very difficult to answer this question before you change this into scientific notation. If you change this to a scientific notation, this will be 3.5 times 10 to the minus what? So I'm moving this is 1, 2, 3, so minus a 3. So that would be, so now you can tell that this is only two significant figures. Two significant figures. So what are the rules for significant figures? We have here a bunch of rules that we need to know, and these rules, please pay attention to them. The first rule is any digit that is not 0 is significant. So anything that is not 0, okay, they are all significant. An example would be 1.234. In this case, we have all of them are significant, okay, because the 1.23 is certain, the 4 might be uncertain, and therefore all of them are significant. So in this number 1.234, we have 4 significant figures. Zeros between non-zero digits are significant. If a zero comes between two numbers, an example of 606, so that O between the two sixes is significant, and therefore this number 606 has 3 significant figures. Zeros to the left, they don't count. Remember this. Zeros to the left, okay, left side, with the existence or non-existence of decimal point, they don't count. 0.08, it has only 1 significant figure. Just like this example. 0.035, 0.0035. Those zeros to the left, those zeros, they don't count, okay? So we have only 2 significant figures. In the example of 0.08, we have only 1 significant figure. What about the zeros to the right? Well, that's a little bit controversial. If there is decimal point, we count them. If there is no decimal point, usually we don't count them. So 2.0 or 2.0, that would be having 2 significant figures, okay? And this number here, 0.004020, it has zeros to the left and right. The left, they don't count. The right do count. So the left, they don't count. So we start with a 4. 4020, that's 4. Here I have an exercise. Let's think about the number of significant figures in each of these examples. How many significant figures are there? Here we have 505. We have we have 2 numbers and a 0 in between. So this is easy. 3 significant figures. Okay, because the 0 comes in between. Here we have 550.5. How many significant figures? We don't care about the decimal point. We have a 0 between 2 numbers. Again, 3 significant figures. Easy. 50505. What do you think? How many significant figures? Are you saying 5? Yes, you are right. 5 significant figures. What about this one? 0.00505. All zeros to the left, they don't count. With or without decimal point, we don't care. Okay? So we start from here, 505. Okay, so that's 3 significant figures. This one, what do you think? Okay, you said, are you saying 4? No, you're wrong. Because the zeros to the left, they don't count. So we only count 505. So that's a 3. This one will be a little bit controversial because we have here zeros to the right without decimal point. If there is a decimal point, we do count the 2 zeros. But in the case that we don't have a decimal point, I will say this one has 3 only significant figures. The book is arguing this number. He says it might be 5 or 3. But to clarify this, let's convert this into scientific notation. How would you write this in scientific notation? There is no, you have to put a decimal point here. So that would be 5.05, okay? And times 10 to the power 1, 2, 3, 4. So that would be 3 significant figures. But if somebody wrote this number as this, 50500.0 now, so now he is more accurate. He's sure about these 2 zeros. So that would be 5.0500 times 10 to the power 4. Actually it's 5.05000, and therefore that would be 6 significant figures. Okay, let's practice this question. Determine the number of significant figures in the following measurements. A, 394. 394 is 3 significant figures. Okay, okay. B, 5.03. That's also 3 significant figures. Number C, 0.714. Zeros to the left, they don't count. So that's also 3. Number D is 0.052. Zeros to the left, they don't count. So this number has only 2 significant figures. Number D, the answer for D is 2 significant figures. And number E, you have 2.720. Zeros to the right, they do count if there is a decimal point. In this number, there is a decimal point. That means the individual who measured this number, he is sure about the 272 and he is uncertain about the 0. But the number of significant figures is equal to the certain and uncertain. And therefore, this number in E, it has 4 significant figures. The answer for E is 4 significant figures. For F, as I said, it's a little bit controversial But for me, because there is no decimal point, I will say that f has only one significant figure. It's the 3. Because if you write this in a scientific notation, that would be 3 times times 10 to the power 3. Okay. Now let us move to the last part of this lecture, which is dealing with significant figures. And this is the most important aspect of this chapter. Okay, so now we know how to deal with significant figures. We need to use that to write the correct answer using the correct number of significant figures in any question that we solve in chemistry. And we can carry this skill for the rest of the course. So we have two situations. We have addition and subtraction. We have also multiplication and division. For the addition and subtraction, we care about the number of decimal places. So if you're adding two numbers, your final answer will take the lowest number of decimal places. Okay? For division and multiplication, we take the smallest number of significant figures. So the rules are different here. Okay? The rules are different. So for addition and subtraction, first we take the lower number of decimal places. Let's throw an example. The example would be 89.332 plus 1.1. If you look at these two numbers, the first one has 3 decimal places. Remember here we don't care about the number of significant figures. We care only about the number of decimal places. In the first number we have 3 decimal places. In the second one we have only 1. So your final answer should have only 1 decimal place. So when you add 89.332 plus 1.1, your calculator would give you 90.432. But that's, if you write this in the exam, that's wrong. You have to round this number to 1 decimal place, that would be 90.4. Another example, if you're subtracting 3.70, which has 2 decimal places, minus 2.9133, which has 4 decimal places, the calculator answer would be 0.7867. But if you look at the numbers that you are subtracting, you have to go with the lowest number of decimal places, and therefore you have to go with the 2 decimal places. Then that answer should be round off to 0.79. 0.79 because it's 0.786. So the 6 is higher than 5, and you round the 8 to 9. Multiplication divisions. Multiplication and divisions is different, because in this case you have to take the smallest number of significant figures. Okay? And an example would be 4.51 times 3.6686. That will give you in the calculator a long answer. You never write the whole numbers. People, they do that all the time in the exams, and that's wrong. You have to round this to the correct number of significant figures. The first one, 4.51, has 3 significant figures. The other one has maybe 5. So you have to go with the 3 significant figures, and therefore you round this to 16.5 only. 16.5 has 3 significant figures. And another example for division is given to you here. Okay? There's something called exact numbers. Exact numbers, you cannot round them. When you say 3 people, okay? Or 3 atoms, okay? Or 1 inch equal to 2.52 centimeter. That's an exact number. You cannot actually play with that number. In this case, an example here, calculate the average of 3 measured length, 6.64, 6.68, and 6.70. When you do that, okay, although if you think about this is division, right? So when you add the numerators, you will have these are all having 2 decimal places, so the answer will be 2 decimal places, and divided by 3. Okay, now the answer will be 6.67, but you might ask yourself, well, I am dividing by 1 significant figure, then therefore the final answer should be 1 significant figure, which is 7. But that's wrong, because the number you are dividing by, which is 3, is the exact number. And in this case, you don't round. With exact numbers, you don't round, you just keep it as 6.67. That's the only case when we don't actually round. This is an example here. carry out the following arithmetic operations to the correct number of significant figures. Let's do that step by step. So we have here a 12.3432. Sorry, that's 12,000. Sorry, 12,000. 3.2. So that's the comma is between 1,000. So that's 12,343.2 plus 0.1893. Now remember, we are doing we're doing addition here. So here we go with the number of decimal places. This number has 1 decimal place. This number has 4. So your final answer should be having 1 decimal place, okay? And when you add these numbers, the calculator answer would give you maybe 3.4 something, but you stop at 4 because we need only 1 decimal place. So that's the first one. 55.67. 55.67, and then minus 2.386. 2.386. Okay, so again, this one has 2 decimal places. This one has 3 decimal places, and your final answer should have how many? It has to have 2 decimal places. You go with the lowest number of decimal places. So that would be 55. But here we have 2 decimal places, we have 3, then this number should be only given in 2 decimal places, and then the correct answer should be 55.28. That's the correct answer, okay? Now let's move on maybe to a multiplication question. Yes, 7.52. 7.52 times, is it times? Yes, 6.232. Well, let's talk about this. When you multiply these numbers in the calculator, your answer, the calculator answer might be it might look something like this: 0625. Okay. But do we write this? Actually, it's 2624640. That's the calculator answer. So what? So what do we do? I see people, I see students writing this all the time in their notebooks and their lab notebooks. That's wrong. Now we need to learn how to do this correctly. Now, for multiplication division, we have to go with the smallest number of significant figures, not the decimal places, remember, okay? So now this number has 3 significant figures. This number has how many? 5? Anyway, we have to go only with the 3 significant figures, right? Only 3 significant figures. And therefore, this would be 52.0. No, this one is higher than 5, so the answer will be 52.1. 52.1. And you can do the other questions as well. And by this, I thank you for attending this lecture. I hope that you benefited from the idea of significant figures and writing the correct numbers of significant figures. So thank you so much and have a great day.